Okay, good morning. Okay, so today we will start a new topic. So we will talk about, so in the following few lectures, we will talk about number theory. But then, let me close the door. But then we won't go into very deep things in number theory. We will talk about some basic knowledge in this field, which allows us to understand a certain encryption scheme called RSA crypto system. So let's do that today. Okay. So I hope to talk about some famous problems in number theory, and then we will talk about some technical things about divisibility. So all of the very basic things you should have learned, or you should have known till your primary school. But then we will talk about this formally. Okay, so first of all, what is number theory? So number theory is the study of integers. So the main character are integers, and then we want to talk about some properties about integers. So this field is once thought to be of pure interest. So it has no application. But it turns out that, so why is it interesting? Because a lot of problems here are very easy to describe, but then it is difficult to determine whether some statement in this area is true or is it false. And so far there are a lot of things, so we will talk about some famous problems that nobody knows how to answer. And then there are also a lot of things that is thought to be difficult in this area, and that this difficult thing leads to application in fact. So crypto system is one of the application. Okay, so let's talk about a couple of famous problems. So the first one is called the Fermat last theorem. So Fermat last theorem says, do we have some integer x, positive integer y, and positive integer z? So x, y, z, they are positive integers. So they are natural numbers, they are positive integers, such that x to the power n plus y to the power n is equal to z to the power n. Okay, so n is also an integer. Okay, so if n is equal to 1, then you will have infinite many solutions. X to 1 to the power 1 plus 2 to the power 1 is equal to 3 to the power 1, right? So if n is equal to 2, there are also infinite many solutions. So because you have 3 square plus 4 square is equal to 5 square, right? So you double every number. So make it, so you will have 6 square plus 8 square is equal to 10 square, right? Or you triple every number, you will have 9 square plus 12 square is equal to 15 square. So you will also have infinitely many solutions for x, y, z. But the question comes when we restrict the case that n is an integer, little n is an integer greater than or equal to 3, then what will happen? So Fermat, a French mathematician, so wrote in his notebook, says that, okay, I got a proof that x to the power n plus y to the power n is equal to z to the power n is impossible to have integral solution when n is greater than or equal to 3. But then in my notebook, the margin is too small. There is just not enough space for me to write down the whole proof. Okay, so I left it. But then nobody really found the proof. So even Fermat has a lot of interesting results that are known to be correct, but he has also a lot of results which is proven to be wrong. Okay, some of the conjectures are wrong. And then for this Fermat last theorem, so after Fermat's story, so it's been open like 350 years. Nobody knows whether it is a yes or it is a no. So whether we can find integral solutions x, y, z, and then n that satisfy this one. Although a couple of cases are known, so for a certain number of n, it is known that it is impossible. But then computer also helps us to verify, to suggest that there is no solution. And finally, so in this year, 1994, so in 1994, American, or an English-American mathematician called Andrew Wiles finally describes a proof that shows that this is impossible. He combines a lot of the latest mathematics techniques at that time and then show that it is impossible. Okay, so now this problem is really solved. Is that okay? So when n is greater than or equal to 3, there will be no integral solution xyz, no positive integral solution xyz that satisfies x to the power n plus y to the power n is equal to z to the power n. Okay? So this is the first famous result. And then there is another one. So another one, this is called the Goldbach conjecture. So what is it? So Goldbach conjecture says, it says that every even integer n greater than or equal to 4 can be written as a sum of 2 primes. Okay, so prime number are, so we all know, right? Prime numbers are integers, positive integers greater than 1, such that it has itself and 1 as the only factor. Okay, so here, Goldbach conjecture is like this. So for instance, if you look at the number 4, 4 can be written as 2 plus 2, prime and prime. Is that okay? If you look at 6, okay, 6 you can write it as 3 plus 3. Is that okay? 1 plus 5 is not okay because 1 is not considered as a prime. So if you look at 8, maybe it is like you can write down 3 plus 5. Is that okay? So if you write 100, so 100 is something. So maybe you can write it down as 47 plus 53. So it turns out that using computer for even very, very, very large number, it is still true. But yet, nobody can show that this Goldbach conjecture is really true. So nobody has found the proof. So some latest results, so this is the latest result. So in 1995, a mathematician called Ramer has shown that every integer greater and every even integer n greater than or equal to 4 can be written as the sum of at most 6 primes. Is that okay? So here we want to show at most 2 or exactly 2. Here, what we know at this point is at most 6. So there's still a gap, but this is some progress. Because primes, there are infinite number of them, and then it turns out that every prime, you can write it down to be something like this, which is actually quite amazing. Okay? Okay? Okay, and then another one. Another one, which, so let me cross this out. Another one is the twin prime conjecture. So if p and p plus 2, so these are 2 integers, are both primes, then we will call them twin primes. Is that okay? So for instance, 3 and 5, they are twin primes. They are a pair of twin primes. 5 and 7, they are another pair of twin primes. So why do we call them twin? Because they are just look really the same, right? P and p plus 2, these two are so for large p, okay, for large prime. So p plus 1 would be, so if p is a prime for large prime p, then p plus 1 will be not a prime because it will be an even number. So the next number that could be a prime will be p plus 2. This is the next one that could possibly be a prime. Okay, but if you look at like 7 plus 2 is not a prime. So if you start from 7, then you need to add 4 before you hit another prime. Is that okay? So that's why twin prime are something that is really like precious. They are close to each other. Okay, so the twin prime conjecture stat says that, okay, there are going to be infinitely many pairs of twin primes. We will never run out of twin primes. Okay, so for instance, if you go to what a very large number, I don't know how large it is. For instance, 89. Okay, well, 89, no, 91 is not a prime. But maybe if you go more, like 101, okay, then you will have 103. This is still a prime. Is that okay? So after 103, then you will still be able to go further to find another prime p such that p plus 2 is also a prime. So this is what the conjecture says. It says that we will never run out of them. You will always find them again and again in the future. But then nobody knows how to answer this one. Is it yes or is it no? Nobody knows. Okay. Now, so some related work. Okay. So for instance, in 1966, so a mathematician Chen Jingren, okay, he showed that, okay, there are going to be many primes p such that p is a prime and then p plus 2 is either a prime or product of two primes. Okay, so this is what Chen has said. So you always find infinitely many pairs of p and p plus 2 such that p is a prime, and then p plus 2 is either a prime or something, we call it a pseudo prime, because it is a product of just two primes. It is really close to a prime, right? A prime has just one prime factor, and then product of two primes, you will have two prime factors. Is that okay? Okay, so this is what Chen has done. So, so if we can remove this case, then this is the twin prime conjecture. But what he showed is a slightly weaker, okay, a weaker version of this twin prime conjecture, and then show that this is true. Okay, and then okay. So here you may think of, for this twin prime conjecture, it is about the distance between two consecutive primes. So the conjecture says that, okay, there will be infinitely many primes such that within the distance 2 you can find another prime. Okay? Okay. Now if you think about this as a distance concept, then there is a new result, very, very new result, by a Chinese mathematician who is now in US, Zhang Yitang, in 2003. He shows that P, there are infinitely many primes P, such that P and P plus some number, okay, some number X, some number D, let's say. So how should I describe? So there could be many, infinitely many primes. How should I describe the result? Let me see. So that, okay, so let's say Pi is a prime P, the I prime, and then Pi plus 1 is the next prime. Okay, so Zhang Yitang says that there are infinitely many primes pi and pi plus 1 such that the distance between this pi plus 1 minus pi is less than 7 times 10 to the power 7. Okay? Or less than or equal to. So if we replace this part by the number 2, then this is the twin prime conjecture. So there are infinitely many pairs of consecutive primes such that the distance is less than a large number. Okay? Okay, previously nobody knows. Okay, previously, so before Zhang Yitang, before this result, all we know is infinity. We don't have any information about the gap between a prime and its next prime. You got it? Okay. But for Zhang Yitang, he says that, okay, you can find many pairs of primes and the next prime such that the gap is small enough. 7 times 10 to the power 7. This is much smaller than infinity, right? Okay. So you find a prime and then which is close to the next prime. And later you can find a prime and then it is also close to the next prime. Is that okay? But what is meant by close is this number. Close. Okay? Okay. Now, so, and then later, okay, later this bound, so let me remove this. So later, this bound is further improved 1 year, just 1 year, by this Polymath project. So Polymath project is a project that is to have mathematicians collaborate through the internet. Okay, so there's a mathematician called Terence Tao. Okay, a very young mathematician. Yeah, Terence Tao in UCLA. He has, because he knows this result, because this result is like groundbreaking. So he invites mathematicians all over the world to join into this project. They work together through the internet, and then they create a project called Polymath. So Polymath has successfully solved a couple of problems. So this is one of the problems. The target is to further, because Zhang has a new technique, a known technique to prove the twin prime conjecture. They try to use Zhang's technique together with what they know to further improve this gap. Okay. Okay, and then what the current best result known, as far as I know, is they can further reduce this gap to a number much smaller, 246. Okay, so that means that there are infinitely many pairs of primes such that the gap is less than or equal to 246. Is that okay? Okay, but still, this is not the ultimate goal that we want. We want a 2 here. Okay? Yeah, but a giant jump. So if you are interested, search for this Zhang Yitang. Yeah, because of his result, he is now one of the academy. So 院士, 中研院院士. So we gave him an honor to be an academician. Okay, so he received a lot of things. And then, so Zhang Yitang has a lot of interesting story. Okay, so search for the web. Yeah, because before this result, nobody knows him. He's been working in so before this result, he's just a lecturer in a university, and before that, okay, before he's invited to be a lecturer at a university, has been working like as a cashier at the Subway sandwich store. Okay, yeah, he has, yeah, and yeah, he's not having a very good relationship with his PhD advisor, so his PhD advisor refuses to write him a recommendation letter. He cannot find a job, something like that. Okay, so there are a lot of interesting stories about this one. So when he sent his paper to a very prestigious mathematics journal, nobody knows. Okay, from nowhere, suddenly there is a person like this one. He has not many publications or perhaps none. Okay, and suddenly get a result by his self-learning. Okay, and then, but it is actually correct, true. Okay, so that's why. Yeah, this is a very amazing story. This is, I think. Okay.